Hello everyone, welcome to our discussion of section 12.1, which will be about the topic of sequences and series. Before we delve a little bit deeper into this topic, let me just give you an overall view of what this topic is. The sequences, any sequence, is a list of numbers such that there is a pattern or connection between the consecutive numbers in this list, and also there is a relationship between the numbers in this list and the location in which they appear. So it doesn't matter that a number is 12, but also it matters in which location it appears. Is it the second number that is 12? Is it the fifth number? Is it the 25th number or the 100th number? So the location of the number within the list is also very, very important in a sequence. So once again, a sequence is a list of numbers such that there is a relationship between consecutive numbers in the list. These are numbers that are one after another. And also, there's a relationship between each number on this list and the location in which it appears. And series is basically it's the summation of the terms or numbers in a sequence. So you might want to add or sum or take the sum of the first 50 numbers in a sequence, because any sequence can be either a finite sequence, a limited number of numbers, or it could be an infinite sequence with indefinite number of elements or numbers on that list. So a series is basically adding chunks or the entire sequence of numbers. So it could be either adding 5 numbers in the sequence, or 500, or 100,000, or all of the numbers, even in an indefinite sequence can be added. But of course, there are certain conditions that have to be met before we can add the members or take the series of a sequence that is infinite. Okay, so let's begin. Now, one more thing before I start writing things down. This topic is very, very important for those of you who will be taking Calculus 2, which is Math 182. So if that course is part of your program of study, you definitely do not want to forget this topic by the time you take that course. In that course, you will delve much, much deeper into this topic. And of course, if you're taking Calculus 3, which is the multivariate calculus, or Math 283, then you'll delve even deeper or more deeply into this topic of sequences and series. But this will be just a basic introduction to this topic. So I'm going to write down what I just said a minute ago, which is a description of what a sequence is. So a sequence is a finite or an infinite list of numbers that have some kind of a pattern, and numbers that have a pattern, that have a pattern between consecutive numbers or they have, or not or, but and have a pattern that have a pattern that is associated with the location of a number within the sequence. And by the time we're done with this section, you know exactly what these mean. Okay, so that's the basic description of a sequence. Here is just a basic example of what a sequence might look like. So the list of numbers 0, 3, 6, 9, 12 is definitely a sequence. So first of all, these 3 dots mean that this is an infinite sequence. And how do we know this is a sequence? We can detect a pattern between these consecutive numbers. So if you take 0 and add 3 to it, you get the next number. If you take 3 and add 3 to it again, you get 6. And so every number in the sequence can be obtained by the number that is previous to it added 3. So take any previous number, add 3 to it, you get the next number. That's the pattern. And this can be considered a sequence. If there's no pattern in the list of numbers, then that is not a sequence. A sequence always has a pattern between the consecutive numbers. Okay, so the other thing I should mention at this point is the notation we use with the sequences. So as we said, the location of these digits is also important, not only what they are, but the location where they appear. So 0 is the first number, 3 is the second number, 6 is the third number. And the way we denote that usually with an A with a subscript. So A1 in this case is 0. And A2 in this case is 3. So the second number in the sequence is that. I'm using the notation or the letters that your book uses, so that if you read these notes after I post them on Canvas and you read your book, they match. And then this one would be A3, that one A4, and A5. Okay, so let's see another sequence. Another example of a sequence would be this one. And this time I want to make this a finite sequence. So notice that there is an end to it. This end could be further along down the road. You could have a sequence that has 1 billion elements in it. But if it ends, if you can put a number on it that it has 10 billion members or numbers in it, then that's still a finite sequence. An infinite sequence will never end. It will have an indefinite number of numbers in it. So this would be a finite sequence. And of course, these members, we can identify them by their location. So A1, or the first digit in the sequence, is 1. A2 is 8. A3 is 64. A4 is 512. And A5 is that, 4096. So do you see a pattern in these numbers? Because if there's no pattern, then this is not a sequence. Surely we can see a pattern, right? Especially when you look at the smaller numbers on the left. each number here is a multiple of 8 of the number previous to it. So 8 times 1, 8. 8 times 8, 64. 8 times 64, 512. 8 times 512 is 4,096. So there is a pattern. And so therefore this is a sequence. And these sequences have names, which we'll look at later in the next sections in chapter 12. But for now, it suffices that we just get used to what a sequence is. Okay, so let's now look at some examples of calculating numbers in a sequence. So here we want to find the first 4 terms and the 100th term of the following sequence. And here's the sequence. And this is called this whole thing has a name. It is called the nth term of sequence. We will talk about all of this in deeper or more detail in the coming minutes. But the nth term of sequence is a formula which can be used to find any number in the sequence. And n represents the location. So n is the location of any number in the sequence. So these formulas, or the nth term of a sequence formula, are extremely important. Why? First of all, they can be programmed in a computer. You can program this so that a computer can calculate any number within the sequence and use that number in some other calculation. Very, very important feature of the nth term of a sequence. The other useful feature of this is that if you're asked to manually find the 100th term of a sequence, in this case, there are 2 ways of finding that 100th term. You can either begin, if you know the first term and the pattern, you can start listing them manually until you reach the 100th number in the sequence. But that will be very, very laborious and time-consuming, right? Or you can use a formula like this, the nth term of a sequence, that you can just simply plug for n, wherever you see n in this formula, with 100, and you're going to be able to find out what the 100th digit is in this sequence. So very, very useful aspect of sequence, or very necessary and essential part of sequences and series are these nth term sequence formulas. Okay, so here we want to use this nth term of the sequence formula to find the first 4 terms and the 100th term, right? So let's do that. So we will say that, and also let me define this an. So note, an refers to any number in the sequence. Okay, so as soon as, right now, it refers to an refers to any number in the sequence because n is free. But as soon as you assign a number to it, then you're finding the number associated with that location in the sequence. So we want to find the first 4 terms. So that means we're looking for A1, A2, A3, and A4, right? That's the first 4 terms. So let's find them. A1 is equal to, in this formula, I'm going to replace n with 1. So minus 1, we're finding the number in the first location, the first number in the sequence. To 1 power, then 1 squared, and then we have minus 1 over 1, right? Simplifying, we have negative 1. Let's find the second number in the sequence. So A2 is equal to minus 1. Again, we're replacing n with 2 this time. Because remember, in a sequence, there's a relationship between a number in that sequence and the location where it occurs. Okay, so that's why we're using the location value here. And then 2 squared. So minus 1 squared is just positive 1. 2 squared is 4, so we have 1/4. Let me use A3. Let me calculate that here. A3 would be, just plug in 3 wherever you see n. So we have minus 1 cubed divided by 3 squared. So minus 1 cubed is minus 1 divided by 9. That's the third digit in the sequence, in this sequence. And then the fourth term would be minus 1 to 4th power over 4 squared. So minus 1 to the 4th is 1 divided by 16. And then we also need to find the 100th digit. So A100, right? Let's replace n with 100 anywhere we see it. Minus 1 to 100th power divided by 100 squared. So then this would be minus 1 to 100th power. That 100 is an even power, so the minus drops out or cancels out. We get positive 1. 100 squared is 10,000, like that. So 1 over 10,000 is the 100th digit in the sequence. Let's see another example of same type. Suppose we want to find, we want to do the same thing. Find the first 4 terms and the 100th term in a sequence. So find the first 4 terms and the 100th term in here, in this sequence, which is a sub n is equal to minus 1 to n plus 1 power, all of that times n over n plus 1. Okay, this is our sequence. Okay, I encourage you to pause the video and do your own calculations and then come back to the video and compare what you've done with this. Okay, so I'm assuming you've done that and you're now ready to see my solution to this question. So A1, or the first term, would be minus 1. Plug in for n with 1. We have 1 plus 1. And then 1 over 1 plus 1. Wherever I saw n, I replaced it with 1. Now, minus 1 squared times 1 over 2. Minus 1 squared is 1 times 1/2 is just 1/2. Okay. Okay, so let's find the second digit in the sequence. So anywhere you see the n, which represents the location of the number we're finding, replace it with 2. So minus 1 to 2 plus 1 power times 2 over 2 plus 1. So minus 1 cubed, right? 2 plus 1 cubed times 2 over 3. So minus 1 cubed is minus 1, right? Because 3 is odd, so the negative sign is preserved. And then we have minus 2 over 3. Okay. So let's find the third digit in the sequence. We have minus 1. Wherever you see n, replace with 3, which is the location of the number we're finding. So we have minus 1 to 4th power times 3 over 4. Minus 1 to 4th power is just plus 1 times 3/4 is positive 3/4. Okay. A4 is the fourth digit in the sequence is minus 1 to 4 plus 1 power times 4 over 4 plus 1, right? Wherever we have n, I replaced it with 4, the location of the number we're finding. So minus 1 to 5th power is that, times 4 over 5. So minus 1 to 5th power is just minus 1, times 4/5 is minus 4 over 5. Now, the 100th digit, A100, right? We're looking for the number that appears in the 100th place in this sequence of numbers. So, once again, negative 1 to 100 plus 1, replace n with 100 in this nth sequence formula, times 100 over 100 plus 1. So minus 1 to 101 power, that 101 is an odd number, so this will be, the negative is preserved, times 100 over 101. So we have minus 100 over 101. Okay. So let's talk about, as we move through this chapter, chapter 12, we introduce various types of sequences. So this next sequence is a sequence we call the recursive sequence. They are very important. And they are a very computation-intensive type of sequence. So the computers would be excellent way of executing a recursive sequence. So recursive sequence is any sequence where any subsequent digit requires knowing what the previous digit is. You might read this and say, well, isn't that how all sequences work? No, just like this one. See, for example, this sequence that we just had in this example, we were asked to find the 100th term, right? But to calculate that term, did we need to know the number that appears in the 99th position or location? No. So this is not a recursive sequence. You can find any digit in this sequence without knowing what the previous digit is in that sequence. But with recursive sequences, we have to know, if you're looking for the 100th digit, you have to know what the 99th digit is. If you're looking for the 99th digit, you must know what is the 98th digit, and so on and so forth. Okay? So what's an example of that? An example, so here is an example of a recursive sequence is an is equal to an minus 1 plus 3. Okay? So that's a recursive sequence, because you want to calculate the fifth term, let's say A5, or the fifth term. Look at what this term is doing. It's saying A5 minus 1 or A4 plus 3. That means if you want to know what A5 is, you got to add A4, the fourth term, plus 3. Well, that means you need to know what the fourth term is. Okay, so that's a recursive sequence. Let's do an example of dealing with a recursive sequence. So here we want to find the first four terms of the recursive sequence that we have here. So it is an equals 1 over 1 plus an minus 1 and a1 equals 1. Okay? So notice that when they're asking us for the first four terms, they have, in recursive sequences, they have to give us the first term. Otherwise, when I want to calculate the first term, I can't do it because it looks back at a term that doesn't exist, term 0, right? In 0 location. Or when you want to calculate the second term, you're going to have to know the first term. And if it's not given, you're not going to be able to answer this question. So with recursive sequence, we are given two pieces of information. The nth sequence, the nth term in the sequence formula, and the first term. Now we can find the first four terms. The first one, which is already been given to us, right? So A1 is equal to 1. We know that, right? So let's find A2. Would be, wherever we see n, we're going to replace it with 2. A2 is equal to 1 over 1 plus A2 minus 1. Let's simplify this. That is equal to 1 over 1 plus A1. Right? A2 minus 1 is A1. So this is saying, hey, if you want to answer this question, you got to know what A1 is. But we are given A1, right? So we're going to plug it in. 1 over 1 plus 1 equals 1 over 2. So that's the second term. So let's find the third term. It's going to be, again, we're going to replace, wherever we have n, we're going to replace that n with the location of the number we're finding. So 1 plus A3 minus 1. What is that equal to? That is equal to 1 over 1 plus A3 minus 1 is A2. So this is saying, hey, if you want to answer what is A3, you got to know what A2 is. Well, we already figured that out, right? 1 over 2. So we're going to plug it in. 1 over 1 plus 1 over 2. Now, this is a complex fraction, and we got to simplify using the method we learned in basic algebra, right? Math 124 and so on. So let's do that. So I'm going to take the common denominator here, Let me do that here in this corner for the benefit of those of you who may have questions about how to find the common denominator. It's very easy. So what we will do is the common denominator here is 2. And so the first number is 1 over 1, right? The denominator here is 1. The second number, 1 over 2. So the common denominator being 2, this fraction doesn't need to be multiplied by anything. But here, the denominator and the numerator have to be multiplied by 2 to give us the common denominator we want. And even though it's the common denominator we want, by multiplying the denominator by 2, we can't multiply the denominator by 2 and not do the same thing to the numerator. So that's 2 times 1. So now we can add those two fractions. So we have 2, right? The common denominator. We have 2 times 1, 2, plus that fraction which didn't need anything multiplied by it. So 1. And of course we have 3 over 2. So then that fraction or that result can be simplified to 1 over 3 halves. Okay, so now this is a complex fraction, which means we need to simplify it. We can't leave it like this. So in the earlier videos, I talked about the easiest way of simplifying a complex fraction, which is note the farthest, the denominator of that one is 1, by the way, so that's why I wrote it in red. So multiply the farthest numbers from each other, 1 times 2, and write that result in the numerator. Then multiply the nearest numbers to each other, 1 and 3, and multiply that in the denominator. And then simplify. So 1 and 1 cancel out. We get 2 over 3 as the third digit in the sequence. Okay? So the fourth digit. The fourth digit would mean that I would have to replace n in this formula with 4. So 1 over 1 plus a4 minus 1. Let's do that. 1 over 1 plus a4 minus 1. So this is saying, this is simplifies 1 over 1 plus a3, right? 4 minus 1 is 3. So this is saying, hey, if you want to know what a4 is, you got to know what a3 is. Do we know it? Yes, we just figured it out up here. a3 is 2 over 3. So let's plug it in. 1 over 1 plus 2 over 3. Just like before, we're going to take the common denominator. So we're going to say in here, we're going to say that 1 is 1 over 1, right? Plus 2 over 3. What's the common denominator here? It's 3, right? So this fraction is happy. It already has the common denominator. But this one is not. So we got to give it the common denominator by multiplying the denominator by 3 and the numerator by 3. Even though we just want 3 in the denominator, we cannot multiply the denominator by 3 and not do the same thing to the numerator. So now we have the common denominator 3. We can add the numbers in the numerator. So 3 times 1, 3. Plus, this one was happy, didn't get multiplied by anything. So 2. And then we have 5 over 3. Okay, so let's put that number in here. So we have 1 over 5 over 3, right? The result of that, adding those two numbers. So now this is again a complex fraction, and we've talked about how best to simplify a complex fraction. So this 1 in the numerator is 1 over 1 actually. Now multiply the farthest numbers from each other and put them in the numerator. Multiply the nearest numbers by each other and put them in the denominator. So that is 3 over 5. which is A4, or the fourth digit in the sequence. Okay. Okay, so far, what we've been doing with all these examples was we were given the nth term of a sequence, and we were asked to find specific numbers within that sequence. But a lot of times, we are given the numbers in a sequence, the individual numbers, like 1/2, 1/2, 2/3, and so on, and 3/5 here, and we're asked to use these numbers in the sequence to find the nth term of the sequence. Very, very important for us to be able to know how this works. So this type of example, where you have the numbers and you want to go back and find the nth term of the sequence, is a very iterative process. In other words, you play with terms until you get it right. So first you look for clues as to guide you to find the nth term of the sequence, and then you modify it. The more complicated a problem is, then you play around with that initial guess until you fine-tune it and get it right. But what I want to emphasize is that it's an iterative process. It's different for every single sequence. So it's something that you'll get used to the more of these you work with. So, and that's the next topic. When several terms, formula for a sequence, when several terms in the sequence are given. Okay, so that's that. So let's jump right ahead and look at some examples and get used to this kind of problem solving. So suppose we want to find the nth term of the sequence. So in other words, this is another way of asking for the formula for the sequence. Formula for the sequence. Okay. So find the nth term of the sequence whose first terms are as follows. First few terms are as follows. Okay, so we have the minus 1/3, 1/9, minus 1/27, 1/81, and ... which means this is an infinite sequence. Okay? So when we're asked for the nth term of the sequence, we're looking for the pattern in this list of numbers, and we want to write a formula to capture that pattern so we can repeat it for any number we want within this sequence. Okay, so looking at this, and this is an easy sequence, we can see that there's definitely a pattern, right? If you look at the denominators, so 3 times 3 you get 9. 3 times 9 you get 27. 3 times 27 you get 81. So it looks like that the denominators are multiples of 3, and more specifically, you can write each base to some power of this whole fraction. So if you minus 1/3 squared, you get positive 1/9, right? And then minus 1/3 to third power, you get minus 1/27. Like I say, this is an easy sequence. A lot of times patterns are not so easy to uncover, but in this case it's easy. And we always want to start easy and build on that and look at more complicated problems. But this, if you look at this whole sequence, you can write it as a power of negative 1/3. In other words, so note, I want to, so this would be the solution part. So after you look at the terms in a sequence, in this case, you note that each term can be written as a power of minus 1/3, right? So that realization, now you set up the first iteration of the nth term of the sequence. In other words, you write this down and you check. You check to see if you can generate these numbers from the nth term sequence. So our first guess in this case, it's an educated guess, but it's a guess because we haven't tested it yet, would be that the nth term of the sequence for this sequence is minus 1/3 to nth power. Okay? So that's our first guess for this easy sequence problem. So now we need to test this. So for n equals 1, which would be the first digit in the sequence, do we get minus 1/3? Absolutely. Minus 1/3 to first power, you get minus 1/3. So that checks out. Okay, so let's test. So I shouldn't, for the sake of your notes, I'm going to write this down. So this is the first iteration for finding the nth term, and let's test it. Let's test it, and we test it by finding the individual, trying to find individual elements. So A1 would be minus 1/3 to first power, minus 1/3. Does that check out? Let me move this down so you can see. Does this check out? Yes. We're okay. So let's see if we're going to get the second number. So A2 would be minus 1/3 to second power. That'll be positive 1/9. Do we have what we have in the sequence? Yes. So once again, we're okay. Let's find the third digit. Okay, so minus 1/3 to cubed. So that'll be minus 1/27. Is this what we have in the sequence? Let's see. Yes, we do. So it checks out. And I personally like to check each one just to make sure, because it's possible that you have this first iteration for the nth term of a sequence, and you test the first two numbers and it checks out, but the third number it doesn't. So we need to continue until we make sure that at least we have tested for all the numbers that are given in the sequence. So, and then minus 1/3 to fourth power. So we have, this is positive over 1/81. Is this what we have in the sequence? Yes. So we've tested it. Therefore, we come back, we can say that this is the final nth term of the sequence after we've tested it. Okay. And of course, I should clarify that in here, n is equal to 1, 2, 3, dot, dot, dot. Okay? So sometimes n can be set to start from 0. It's fine. Sometimes you can force it to start at 0. But we're making it clear here that n, or the location, starts at 1, not 0. Okay? So you can see clearly that there is a connection between the location of these numbers in the sequence and the value of the number in the sequence. So the second digit is the second power, third digit becomes the third power, fourth digit becomes the fourth power. Okay? All right. So let's see another example. Here we want to find the nth term again. Of the sequence. And so let me make this clear again, since we're introducing this topic. I don't mind to write that this is the formula. What they're asking really is the formula for the sequence. Okay, that's what they're asking us. Find the nth term of the sequence whose first several terms are given. Okay, and here are the first terms. That and dot, dot, dot. Okay, so this is once again an infinite sequence. Okay, so one thing that, if I see this sequence for the first time, let's look at the previous example. So what was, if you see some sequence like that for the first time, the first thing that should catch your eye is that you have a mix of negative and positive values. And the second thing, of course, is the fraction and how they're connected. But it's a mix of negative and positive values. Here, if you look at this sequence, they're all positive. But what should catch your attention is that you have a mix of fractions and whole numbers. Right? So let's just, as a preliminary way of finding what's the connection between these digits, just label these. So this one is A1, right? That's the first digit. Or so for this one, so n is equal to 1 for that one. N equals to 2 for this one, right? That n representing the position of this number within the sequence. N equals 3 for that. N equals 4 for that. N equals 5. N equals 6. Just doing this, notice a pattern emerges, right? Because the first number for the odd numbered positions, 1, 3, and 5, the number is equal to the position value. Now that's interesting, right? But for the even numbered positions, 2, 4, and 6, you have a fraction where the n, or the position number, appears in the denominator. So this is the fourth digit. The 4 is the denominator of that. This is the sixth digit. 6 appears in the denominator. But if it's an odd position, or 5, the number itself equals to the position number. So that means if I have n equals 7, right? Which is not listed. But if we had, that number would have been 7. If we had an 8th number, which is an even position, right? The 8th position is an even position, so that number would have been 1 over 8. So there's definitely a pattern here, and we've already discovered it. We know we can write the rest of this sequence, but that's not what this problem is asking. The problem is asking, find the nth term of the sequence. We want the formula, because we know there is a pattern, and we've discovered what that pattern is. Okay? So let's find then other clues for finding the nth term of the sequence. So then we know that, so let me actually, before doing that, let me capture that what we've discussed. So we've learned that an, that means any term in the sequence, is equal to n if n is odd. Okay, we've learned that. And a sub n, that means any term in the sequence, is equal to 1 over n if n is even. Okay, so what is the 10th digit in the sequence? 1 over 10, because it's 10 is even. What is the 19th digit in the sequence? 19 is odd, so a 19th is 19. Okay, but we need to use this information or something more to find the nth term of the sequence. And by the way, so the solution starts here, right here. Okay, so the other thing that should catch your attention, in addition to this, is that the fact that you have a mix of fractions and whole numbers, it suggests that we have somewhere in the nth term of the sequence that we're trying to find, somewhere there we must have a negative power. And because in mathematics we do not keep negative powers for the most part, we like to rewrite the expression without the negative power, that's why we end up with 1 over 2, 1 over 4, 1 over 6. In other words, what I'm saying is that the insight into that is that 1 over 2 can be written as 2 to negative 1 power. You see that? 1 over 4 can be written as 2 to negative 2 power. That's 1 over 4. If you rewrite this with positive power, you get 1 over 4. But can we say that about this one? No. There is no power of 2, negative power of 2, that would give us the 6. Nonetheless, the fact that we have fractions suggests the existence of a negative power. Okay, so I just wrote this to explain how we might have these fractions written in terms of a negative power, but we don't need these. Okay, so now let's find in how we can basically find the right sequence for this. So let's write down a first iteration. Suppose, so as a first guess for the nth term of the sequence, so that's the first guess. Let's say that a sub n is equal to n, and so minus 1 and plus, let's see, plus n. Just a wild guess. Let me try that, because the fractions tell me I should have a negative power. So, and let me try that. So if this is true, if this is the sequence, nth term of the sequence, I should get these numbers, right? Let's see if we do. So for the first digit, that would be A1. Testing A1. So we have 1 to negative 1 plus 1. That'll be 1 to 0 power, and we get 1. Very good. We got that. Okay, so far so good. Let's see if we're going to get, for the second term, if we're going to get 1/2. So, testing A2. So we have, that would be 2 here, raised to negative 1 plus 2, right? So 2 minus 1, that'll be 2 to 1 power, we get 2. Is 2 equal to 1/2? No. No. So because of that, this is not the correct nth term of the sequence because of this result. I want to show you that this is an iterative process. You need to go through iterations of a first guess for that sequence, nth term of the sequence, until you get it right. So let's use a second guess. So as a second guess, of course this is going to be an educated guess. It's not just throwing darts blindfolded. We've talked about these two and the fact that the fractions suggest we should have some kind of negative power. So let's see, because I want some fractions, so I need to preserve that negative. If I had in this operation, if I had some, instead of 1, if I had negative 1 as the result, I would have gotten the 1/2, right? So I can use that to think of another way of writing my nth term sequence. So if this was 2 to negative 1 power, I would have gotten 1/2, because 2 to negative 1 power is 1/2. So let's see how I can modify this first guess so that I can end up with a negative power for 2 next time around. Let's see if this would work. So the nth term, n to minus 1 power, so I'm going to keep that, but this time I'm going to raise this to n plus 1 power. Okay, so I kept this part, but instead of adding n to it, I'm raising it to n plus 1, because if you notice, we have, for even numbered digits, the second digit, the fourth digit, the sixth digit, we have a fraction. So I want this negative 1 preserved for even numbered digits in my sequence. Okay? So I don't want it preserved for odd ones, so I want it preserved for even numbered. And this is the way to do it. Because if you have an even number digit, a number in the sequence which is in the location which is even numbered. So location 2 is even numbered, location 4 is even numbered, location 6 is even numbered. With this modification of this original guess, we can maintain the negative 1 power for numbers that appear with even location number. Because if you're looking for the second digit, then you plug in for n with 2. 2 plus 1 is 3, which is odd, which means this negative 1 is going to be preserved, and that's what we want. So let's test this. So I made this modification. Now let's test using this, testing. So let me write this with a different color. I don't want it mixed. So that was the first guess up here, and this is the second guess. This is why this is an iterative process. You shouldn't be frustrated if the first one doesn't work, like it didn't in my guess. But you should modify it to resolve the issues and get the sequence that you want. So testing A1, I'm going to plug in 1 for n. So 1 to negative 1 power 2, 1 plus 1. What do I get? I get 1 to negative 1 squared. Negative 1 squared is 1. So 1 to 1 power is 1. Did I get the first digit in my sequence? Yes, we got it. Okay. Let's see if we're going to get 1/2, which is the second digit. Okay. So testing A2. I'm going to plug in for n with 2 in here. So 2 to negative 1. So far, so good. And then raise that, not multiply it, raise it to 2 plus 1. What are we going to get? We're going to get 2 to minus 1 power to third power. Okay? Now 3 is odd, so this negative 1 is preserved. So we're going to get 2 to negative 1 power, which is 1/2. So it checks out. We got the 1/2. So let's see if we're going to get the third digit, which is 3. So testing A3. I'm going to plug in for n with 3. 3 to negative 1, and then raise that to 3 plus 1. So 3 to negative 1, raise that to fourth power. Now negative 1 raised to fourth power is an even numbered power, so negative 1 drops out. It becomes positive 1. So 3 to first power, which is 3. Is this what we have in the third position? Yes. So it works out. I'm gonna test the 1/4, and I'm going to leave the testing of A5 and A6 to you guys. So I'm going to test for A4 to see if I'm going to get 1/4 next. Okay, so testing A4. So I'm going to plug in for n with 4. 4 to negative 1 power raised to 4 plus 1. Okay, what are we going to get? We're going to get 4 to negative 1 power raised to fifth power, right? Fifth power. 5 is odd, so minus 1 raised to any negative number raised to an odd power preserves this negative. So we end up with 4 to negative 1 power, which is 1/4. So, which is what we were looking for. So this definitely looks like the nth term of the sequence we were looking for. So I'm going to box this. If you remember that I said we need to check with all the terms that we are given, you're absolutely right. So, but I want to leave it up to you guys. So please test this nth term of the sequence for A5, and A6. Just verify it on your own and see if you get 5 and 1/6. Okay? All right. One of the sequences, in any discussion of sequences and series, there's a famous sequence called the Fibonacci sequence. I just want to mention it because you're going to read about it. It is a neat sequence. And so I'm just going to mention it as a note. So this is the Fibonacci sequence. This is a famous sequence such that here are the numbers in the Fibonacci sequence. So you have 1, 1, 2, 3, 5, 8, 13, ... So if you look at this sequence, the first 2 digits are always 1, and the third digit, or the next digit after the first 2, is obtained by adding the previous 2 digits. So 1 plus 1, 2. 2 plus 1, 3. 3 plus 2, 5. 5 plus 3, 8. 8 plus 5, 13. 13 plus 8, 21 would have been the next digit. Then after that, you'd have 34 because 21 plus 13 would have been 34, and so on and so forth. That's Fibonacci sequence. So that's the first few terms in the sequence, but we also have a formula for it, or the nth term of the sequence for it, which is a sub n is equal to a n minus 1 plus a sub n minus 2, right? This is the same thing as saying add any previous 2 terms to obtain the current term. Okay, so this is the current term, this is the previous term, and that's the previous to previous term. Exactly what we said above here. So to obtain 2, you'll have to add this number and this number. To obtain 3, which would have been the current term, you would have to add this 2, which is that term, with this term, which is that term. Okay? Again, notice how the location of each number is tied to the numbers in the sequence. So after all this discussion about sequences, we are finally reaching the topic of the series. Partial series in this context means the addition or sum of some terms in a sequence. So instead of saying obtaining the sum of these terms in a sequence, we say obtain the series of that sequence. Okay, and if you're finding the sum of all the terms in a sequence, then you just say that's the series for the sequence. But if it's the sum of certain numbers within the sequence that you're finding, you're finding the partial sum or the partial series for the sequence. So this is just a little bit of terminology for this topic. Okay, so we have the partial sums, that's the series, partial sums or series of a sequence, i.e., let me write it underneath this, i.e., or in other words, partial series. Okay. So let's briefly explain some things, some notations, some concepts before we see some examples. So for the sequence A1, A2, A3, A4, A5, dot, 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 all the way to AN. The partial sums are S1 equals A1. So if you add the first term with itself, you get itself, right? Sum of the first term is A1. Sum of the first two terms, sum of the two terms, S2. S2 would be A1 plus A2. That's sum of the first two terms. Okay? You don't have to add the first terms. You can start adding, say, the fifth term all the way to the maybe 16th term if you want to. But the formulas would adjust. Okay? So this is a very large area in mathematics, and I want to stick with only those areas that your book talks about. But we'll see how deep this chapter 12 goes into this stuff. Okay, so and then the sum of the first three terms in the sequence, of course, then will be A1 plus A2 plus A3. So at this point, I want you to pay attention to the notation that S1, S2, S3 represent the sums or series, partial sums or partial series of any sequence like that, and so on. And so on. Okay? So the other thing you should know about this is the sigma notation. This notation, which comes from the Greek letter sigma, is used extensively in connection with series. So we should be familiar with what it looks like and what it means. So the sigma notation, so given a sequence like this, A1, A2, A3, A4, then we can do this. We can say sigma, this is the capital letter sigma. Let me quickly write here. So on a piece of scratch paper here, I want to explain what this is. Because if you've taken the statistics before this, you know that this letter is also called sigma. And now we're saying this letter is called sigma. Okay, so which is it? Is this sigma or that sigma? They're both the same letters, but this is the lowercase in Greek alphabet for sigma. This is the capital sigma letter in the Greek alphabet. Okay, this is the capital letter. This is the lowercase letter in the Greek alphabet, but they're both sigma. In statistics, you'll see this. Here, in connection with series, you'll see this one. Okay, so then this is the letter sigma. It means sum. So let me call this AK, and then is equal to A1 plus A2 plus A3 plus dot, 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 plus, let's say, AN. And a very crucial thing attached or connected to this sigma notation is the index. The index is, let's call it K. In this case, it's being called K. This K is not fixed. It can sometimes be, a lot of times actually, it's called I. So A sub I rather than A sub K. And I'm trying to be consistent with your textbook, so I use K because your textbook uses K. If they used I would have used I. But the significance of it is that K represents the subscripts you see in the actual sequence, and you can increment it to go from anywhere to anywhere. So we can increment this to go from the first digit, which would be A1, all the way to the nth digit. So n could be anything. If you stop at 50, then this goes from 1 to 50 and adds all the numbers, all the 50 numbers there. If you go from 1 to 12, then that will just add 12 terms, A1 through to A12. If you go 1 through 5, it'll add 5 terms, first term through the 5th term. Okay, so that's one thing you should know. But what is the property, the other thing we're interested in, what is the property of this notation? So let's talk about that. So for now, I just introduced this notation and talking about what it means. It means the addition or sum of the terms or numbers in a sequence. That's all. So let's see what properties this has. Okay, so properties of sums are as follows. Number one, if you have a sum formula as follows, k equals 1. Again, I'm using the notation that your book uses with k. Usually it's I equals 1 to something, but your book uses k, so that's what I'm doing. K equals 1 to n. Then if you have in parentheses after it, after the sigma, if you have a in parentheses ak plus bk, then this is the same thing as this. Like that. Okay, so this is one of the properties of the sum notation. Like that. Okay, so this left side is equal to that. You can separate them and add them is the same thing, as if you added the sequences and then applied the sum. It makes no difference. Okay, the second property is this one. We have the same property for, you guessed it, subtraction. This was for addition. We have the same thing for subtraction as well. Like that. And the next property is what if we have a constant out here? So if we have a constant multiply, you can pull the constant out and put it in front here, which a lot of cases it simplifies the expression. All these three properties are really helpful when you really start working with series in calculus 2 and 3. They are very useful properties. So this would be this one. It is sigma from this. And notice I'm going to write this in red so it catches your attention. C, that's a constant, some number, 5, -2, something, some constant, times AK, that is equal to, C can be put in front like that, times sigma k equals to 1 to n ak. Okay, so we can actually use a thicker marker here to box all of this. Very important properties when you deal with series. That one and that one. Okay. Okay, so So let's see an example of these. Just the concept, not necessarily the notation I'm talking about. The notation you'll really use, we'll use it a little bit here, not much. We'll use it a little bit, but in Calc 2 and Calc 3 you'll use it extensively. So here we want to find the first six partial sums, S1, S2, S3, S4, S5, S6. So this is basically saying in the sequence we have that I'm going to write down in a minute, find the sum of the first term with itself, some of the first two terms, the first three terms, four terms, five terms, and so on. Okay? So find the first six partial sums of the sequence this is the sequence, 1 squared, 2 squared, 3 squared, 4 squared, dot, 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 like that. Okay, so here's the solution. So the sum of the first number with itself, which is 1, so S1 is 1 squared equals 1. That's it. Okay. S2 is this plus that. 1 squared plus 2 squared, or 1 plus 4, or 5. S3 would be the sum of the first three terms, 1 squared plus 2 squared plus 3 squared. So we have 1 plus 4 plus 9, or 14. Okay, and S4 is 1, adding those, so then we have 1 squared plus 2 squared plus 3 squared plus 4 squared. So we have 14, which is all the way to here, 14 plus 16, or 30, right? Like that. So we know, but they're asking for the sum of the first six partial sums. So they're asking us to find S5 and S6. But of course, this sequence has a pattern that is really, really easy to see, right? So the fifth term would be 5 squared, the sixth term would be 6 squared, and so on. So we can take advantage of that. So we know that A5 is 5 squared. Therefore, S5 would be 30 plus 5 squared. So that's 25 plus 30, 55. And finally, we know that A6 is 6 squared. Therefore, the sum of the first 6 digits is 55, which is the sum of the first 5 digits, plus the 6th digit, which is 36. So we have 91. Okay. Okay, so now what we did with the sequences, which is first we were given a sequence in the nth term of the sequence, or the formula for the sequence, and we were asked to find the first 4 digit or the 100th digit, right? We did that in the beginning of this section. Then we also did a few exercises on, given a set of digits in a sequence, can we find the nth term or the formula for the sequence? We did a couple examples like that. With the partial series, the same thing is true. So given given the individual members of the series or the sum, we can go back and calculate a formula for the sum. Okay, so let's do that. So in this example, we want to find the nth partial sum. Not nth term of a sequence, but the nth partial sum. Very important. In other words, what this is saying, i.e., find the formula for adding the terms in a sequence. Okay. Find the nth partial sum of the following sequence. Okay, so here's the sequence. We have that as an equals 1 over n plus 1 minus 1 over n plus 2. Okay, so now the way we would, let's see, do we? Oh yeah, so we are given this sequence and we're asked, so this is the nth term of a sequence that we are given, and we are asked to find the partial sum for this. So in other words, for the sequence that results from this nth term, we want to have a formula for the sum of those numbers. Okay? So whenever you have the nth term of a sequence given to you, to find the partial sum, first list the first few terms of the sequence. Because we are given none of that, we need to generate them. So let's generate the first few terms, the first 3 terms of this sequence. Okay, that's easy. So solution, first, generate a few terms in the sequence. So that's what we need to do. So I have those A1 equals, so plug for n with 1 is equal to 1 over 1 plus 1 minus 1 over 1 plus 2. So we have 1 over 2 minus 1 over 3. Now normally I would take the common denominator here and combine and simplify and combine this, right? But not in this case. In this case, believe me, it's better if you leave it like that. So we don't want to take the common denominator and simplify this. Let's leave it like that, and you'll see, in a minute, you'll see why. So A2, let's calculate A2 is 1 over, then we're going to substitute for n with 2, 2 plus 1 minus 1 over 2 plus 2. So we have 1 over 3 minus 1 over 4. Okay, notice what's happened. Again, I'm not going to take the common denominator here, but compare this result with that. There's going to be a pattern that is going to emerge. And then let's find the third term. We have, so substituting for n with 3. I think the screen is a little bit fuzzy, so let me focus this. Okay, that's better. Oh, that's sharp enough. So 1 over 3 plus 1 minus 1 over 3 plus 2, right? So what do we get? We get 1 over 4 minus 1 over 5. Do you see a pattern? 1/2 minus 1/3, then positive 1/3, minus 1/3, negative 1/4, positive 1/4, negative 1/5. And I'll bet if we continue, we get positive 1/5 and so on. So there's definitely a pattern here. So now that we have a few terms from the sequence, then let's calculate. So that's the first thing we do. Second, let's calculate the partial sum. That's what they want, right? Find the nth partial sum. But nth partial sum means find the formula for partial sum. But we're going to do it. What we're doing is doing the same thing, but for a specific sum. In other words, we're going to calculate the partial sum for the first three terms. Okay? But our objective is to find the general formula for any partial sum for this sequence. Okay? So the partial sum in this case would be, so let me make that clear, that second, find the partial sum for the first three terms, which we just calculated. Three terms of the sequence. Okay? If we do that, we will get, so A1, A2, A3. So what is S1, I'd say S3. That's the partial sum for the first three terms. It will be A1 plus A2 plus A3, right? Okay, so we have A1 as that, A2 as that, and A3 as that, right? Let's add those results. We're going to get, 1/2 minus 1/3, that's A1, plus 1/3 minus 1/4, plus 1/4 minus 1/5. Okay, so this is A1, this is A2, right? That's what we're doing, and we're adding them. This is A2, and this piece is A3. Oops, let me move this over here, like that. Okay, so what is happening then, if you add these, the terms drop, so this minus 1/3 and this plus 1/3 add up to 0, these two. This minus 1/4 and this 1/4 add up to 0. So what do we end up with for the first three terms? So for the first three terms, the partial sum is equal to 1/2 minus 1/5, right? Right? So 1/2, the first term, notice what is happening. The first term, the 1/2 from the beginning persisted through all of these additions. So when we added all these three terms, the 1/2 stayed, but those middle ones and the last one persisted. They stayed on in the final result, right? So using this partial sum, so the first three terms, for the first three terms, the partial sum is this. Thus, the partial sum for the entire sequence, that's this sequence, for this entire sequence, can be formulated in the general form like this. We can say that partial sum, that's Sn, equals 1/2 right? I'm just looking at that. Minus 1 over, how can we generalize the 5? We got minus 1, 5 for the partial sum for the first 3 terms. But for the nth term, so 5 is 2, right? 2 more than, what is 3? 3 is n, the location where the sum or the series ends. So 2 more than that n. So instead of 3, we have n because we're generalizing. We did what you see here is very important. First, you find a specific partial sum for a certain number of terms in the sequence. Then you use that result to generalize to the whole sequence. That's what we're doing here. So 3, we can now generalize to Sn. 1/2 stayed from the first term, so 1/2 is there. Minus 1 over 5th, the last term is 2 more than the n, or 2 more than 3. So n plus 2. So that is our partial sum formula for this sequence. Okay, I hope it's making sense. Whenever you're asked to find the partial sum for a certain sequence, you want to add or obtain the partial sum for a few terms in the sequence. Then see how that partial sum changes, and then use that to write down the partial sum formula for the entire sequence. And of course, I should mention that here n is 1, 2, 3, ... right? So n is incremented from 1, 2, 3, and so on. So let's see another example of calculating the sums or series of a sequence. We want to find the sum, this sum. Here is where that notation comes in handy. J equals 1. This time we're using J as the index. 1 to 100, and here is minus 1 to J power. So now the location of a term becomes the power of that term. See, that's the connection between the location of that term, any term, and the value of that term. And they want us to find the sum of the first 100 terms. Okay? Obviously, we're not going to write down and add all these 100 terms, right? So what do? Well, just like what I mentioned earlier, we write down the first few sums. The first few sums, and see what pattern is there, and then use that pattern to write down the sum that we're asked for. So let's write down the first few sums for now. So here's the solution. So first, write down, or calculate, I should say, calculate the sums of the first few terms, just to uncover the pattern in the sum or series. They're both the same thing here, sum or series. Okay, so to do that, so we say that for S1, right? For S1, it'll be J would be 1, right? So minus 1 to first power, we have negative 1. So S1 equals negative 1. right? So S2 would be negative 1 squared and plus, and S2 is the sum of the first two terms, right? That would be negative 1 plus, so I should correct this. So negative 1, well, let's do it this way. I wanna. It's better if I put the S1s here, and it's more clear, I think. So I'm going to get rid of these. So then minus 1 squared, it's going to be positive 1. Therefore, S2 is equal to S1 plus 1, right? S2 is equal to negative 1 plus 1 equals 0, right? So for J, I guess I should have, it would be better if I did it like this. I think it will be more clear. It'll be more clear if I said if J equals 1, then we're doing that. If J is equal to 2, then that. Yeah, that's more clear. And then I will clean this up before I post my notes on Canvas, okay? I won't leave it like that. I will clean this up. But for the video, I can't do anything about it. So if, let's do it all the way until 5. If J equals to 3 in here, right, in this formula, then we have minus 1 to cube, which is minus 1. So S3 would be the sum of the first three terms, negative 1 plus 0, negative 1, S2 plus S3. So 0 plus negative 1. You can either start from the beginning, S1, negative 1 plus 1 plus negative 1, you get the same thing. Or you can just add what you have to this. So it'll be 0 plus minus 1, negative 1. So notice the pattern, negative 1, 0, negative 1. So let's do a couple more just to be sure that we've uncovered the pattern. So if J equals 4, then negative 1 to 4th power, that'll be 1. Then S4 would be all these four numbers added together, right? You can do negative 1 plus negative 1 plus 1. You'll get 0 again. Or you can just say negative 1 plus 1. It makes no difference. Negative 1 plus 1, you get 0. Do you see the pattern? Negative 1, 0, negative 1, 0. Let's do another one. So if J equals 5, then we have negative 1 to 5th power, or negative 1. And this is, so S5 would be 0 plus negative 1, and negative 1 plus 0. So we get negative 1. Okay, so notice the pattern. Negative 1, 0, negative 1, 0, negative 1, right? So this pattern is clear that when, now take a look at the location of the sum, or the partial sum index, right? How many numbers we're adding and what connection that has with the value we're getting. If we're adding an odd number of values in the sequence or in the sum, we're adding one number, we get a negative 1. An even number, 0. Odd, negative 1. Even, 0. Odd, negative 1. Do you see? There's definitely a pattern. So if you're adding 100 digit, which is an even number, what do you expect to see based on this analysis? 0, right? Because 100 is an even number, and we've just uncovered the pattern in this partial sum. If you're adding, in this partial sum, if you're adding even numbers from it, then you're going to get 0. So note, so let me write that here. let's see. So adding odd number of digits leads to, we've just uncovered it, to -1. And adding even number of digits leads to 0. Okay, so because we are adding 100 digits from the sum, then the partial sum is 0. S100 equals 0. Okay, like that. All right. So another, these are examples that were in, I picked some examples that are representative of what I saw in your book. So your book has other additional examples that they have solved. Please also look at those in your book, in addition to the ones that you see in the video. And that will give you easily over a dozen examples to look at. And so here's another example. It says, write the sum without, this is the key, I should have written it in red, without using the sigma notation. So here is what they have. This is what they give us. Okay, so they want us to write this without this sigma notation. Notice the index k is going from what to what? It's going from 6 to 9, right? Not from 1 to 3 or 1 to 5. So it's not starting from the first digit in the sum. It's starting from the 6th digit in the sum, and it's going up to 9th digit. So they're saying add these 4 digits. The digit that is at location 6, the digit that is at location 7, the digit that is at location 8, and the digit that is at location 9. Okay? Add those 4 digits and write it without using the sigma notation. And we can do that, right? So that's what they're asking, to write this sum without the sigma notation. We can easily do that. So we have, we can just plug in, right? So we have S6. Well, I shouldn't say S6, so because it's not the sum of the first 6 digits. So let me just leave this out. I'm just going to plug in. So this would be equal, the left-hand side would be equal to 6 times 6 plus 3, right? That's for that. Then the 7th seventh digit in the partial sum. So 7 times 7 plus 3. The 8th digit in the partial sum, 8 times 8 plus 3. And finally, 9 times, so plus 9 times 9 plus 3. Okay, when we add all of those, this is what I have. I ended up with 54 plus 70 plus 88 plus 108. Okay, like that. And so let's calculate this. So we have 4, 12, and 20, and 2, and 10, and 17, 22, and 220. I want to check that with my calculator just to make sure that I didn't make any error there. So let's double check that. Like that. Okay. So we have 54 plus 70 plus 88 plus 108. Oh, 320. So I'm glad I checked. So 320. Like that. Okay. So let's do another example. This time we're going the opposite. This time we are given terms in a partial sum, and we want to use that to write the sigma notation or the generalized notation using sigma for the partial sum. So here we want to write the finite sum. Remember we had finite and infinite sequences. We also have finite and infinite series or sums. So this one says write the finite sum using, this time it's using, because the previous one says without the sigma notation. This time we want to do it using the sigma notation. Using sigma notation. Okay, and here is the sum that we have been given. I'll try to fit it here. 1 over 2 natural log of 2. Remember natural logs? We haven't dealt with them for a long time, right? We dealt with them in pre-calculus 1, but not so far in this course. Minus 1 over 3 natural log of 3 plus 1 over 4 times natural log of 4 minus 1 over 5 natural log of 5 plus plus 1 over 100 natural log of 100. So this is why they're saying the finite, right? The finite sum, because it ends, right? Plus that's the last term in the sum. Okay, I'm sure you can see clearly that there is a pattern here, right? So that is the, let's see, so if we have, so that's the first term, right? So this is S1, and I don't want to call it with that S1, S2, but this is the first term in the partial sum, but the numbers 2 is 1 plus 1, right? So whatever the location, let's call it K because your book calls it K. You can call it anything, N if you prefer. But this number here is 1 plus that. This is the second location. Again, these numbers are 1 plus 2. This is the third number in the partial sum, but these numbers are K plus 1. Do you see how it works? first location, these numbers are 2. So 1 plus 1 gives us 2. This is the second number in the partial sum, but this 3 means 2 plus 1. This is the third number, 3 plus 1 is 4. This is the fourth number, 4 plus 1 is 5, and so on. So that one will be 1, 2, 3, 4. So that one would be the 99th one. Okay, so that one, this is that. So that would be 99. Okay, so let's write it down. Here's the solution. And notice the alternating algebraic sign. It starts with positive, then negative. For the second term, it's negative. So then the power should reflect that. So we have sigma. We have to be careful here. I'm going to call it k because your book calls this index k for some reason. Usually I've seen it called with the letter I, but this is letter K. So K beginning with 1, and then it's going all the way to, so that is the first term, and that is 2, so this is 100, so we're going to 99 here. Then the alternating algebraic sign means we should have a negative 1 here raised to some power. For the first term is positive. So for k equals 1, it's positive. So k plus 1, right? Then if k is 1, then minus 1 to second power is positive. If k is 2, 2 plus 1, it's minus 1 to third power is negative. So it starts to make sense. And then all of that times, of course, the main fraction, right? Which is 1 over k plus 1. So k plus 1 times natural log of k plus 1. Like that. Okay? So here is the partial sum using sigma notation for this. So this is the partial sum formula for the whole partial sum. Okay. Okay, let's do another example of the same kind. Okay, these are really neat. So we have So we want to, in this example, we want to write the finite sum using sigma notation again. Sigma notation, and here is the partial sum we are given, 1 plus x squared plus x cubed plus ... plus x to 100 power. Okay, so it's really, this one is really easy to see, right? Solution. We're going to write the same thing using sigma. So we'll say sigma, or sigma. Again, I'm going to call it, let's call it something else. We don't have to stick with k. Let's this time, because you guys need to get used to different indices for this sigma notation. Let's call it n. So this time, so if I have sigma x to n power, that's clear, right? But that would be, if I have, for the first term, I would get x, not 1. So how can I manipulate this to get what I want, which is this list? So if I start this from 1, n equals 1, then the first term will be x, not 1. So I need to pick n such that I get 1. What is the only thing, the only power here for x that will give us 1? 0. So I have no choice but to start this n from 0. Now x to 0 power is going to give me 1. Then x to first power for the second term, right? For the n equals 1 for the gives me the second term. Okay, let's write it down because I want to make sure that you see how we need to change this or leave it alone. Let's see. So x to 0 power is going to be 1. X to first power, it's going to be x. X squared, it's going to be x squared. But my point is that, see, that one, this one is the first number. So here, this is n equals 0, n equals 1, I should have done it that way, not this way. But, and so on. So on this, in here, we can continue on and on. But the more important thing is that look at the power, the connection of between the power of each term and the location of it within the partial sum. 0, 1, 2, 3, right? And so on. So if you continue, then this will be n equals 100, right? So then the top part of this, because we need to, just like the previous example, we need to determine what is the lower, what are the lower and upper bounds of this sum. This is a partial sum. What the lower bound was 1, k starting from 1, and then going all the way to 99 for that problem. But for here, then it has to start from 0 and it has to go all the way to, the upper bound is 100. So let's complete the formula here like that. Okay. So this is how we reason about finding the partial sum formula for that series. Okay. I hope this is clear, the procedure that we got to this point. We got to be careful because this pattern was easy to recognize, right? X to some power, it was clear. But this number was a little bit tricky because if you start from 1, you get x, not 1. So, and the upper bound, you got to be careful what is that where that number has to end. Okay? All right. Let's do another example. Here, we want to find a formula for the nth term of the sequence. Oh, we haven't done these in a few minutes, right? In maybe half an hour. So we did a few of these in the beginning of this video, but now here's another one. So find the formula for the nth term of the sequence. And there's a hint they give us. Hint. Write each term with powers of base 2. Write each term with powers of base 2. And here's the sequence, or individual digits in the sequence, because we need to find the formula for it. So they have to give us the individual terms in the sequence, which are as follows. Square root of 2, 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 like that. Square root of 2, square root of 2, square root of 2, square root of 2. Okay. At first, this looks a little bit confusing, but take a look at this hint. This simplifies things, right? Hint, write each term with powers of base 2. So let's do that. That's actually very helpful hint here. So square root of 2, we can write that as, so using this hint, let me bring it into this screen. So using this hint, we're using that hint here. Square root of 2 can be written as 2 to 1/2 power, right? The power on the inside divided by the index, which is 2. So what about this one? Well, that one will be square root of 2 square root of 2. This is simply 2 to 1/2 power. And every time you embed another radical expression within another radical expression in this multiplication form, you are multiplying their power, their rational powers. So this will be, for this one, this will be 2 to 1/2 power. So this will be so this will be 2 to 1/2 power, right? For this one, it will be 2 to 1/2 power times 2 to this 1/2 times 1/2. So 2 to 1/4 power. And that's because this one is 2 to 1/2 power, but it's within another radical, so that's to raise to 1/2 power again, which is 1/4. And this one, oh, by the way, so let's combine these. So we should add those powers. Take the common denominator, you get 2 to 3/4 power. Let's do that for these two, the other two. So square root of 2 over a square root of 2 over a square root of 2. So this first one, it's going to be 2 to 1/2 power. The second one is within an embedded radical expression, so it'll be just like this, 2 to 1/4. Because this one, like that one, is 2 to 1/2 power, but it's within another one that has 1/2. So they get multiplied. So 2 over 1/2 power. And guess what will that do? So multiply, that's within another radical, so that'll be 2 to 1/8 power. Okay? And then if you add all of those, take the common denominator. Common denominator would be 8, and then that would be 4 plus 2, 3, 7, and 7/8. Let me double check that. So 4 plus 2, not 3, plus 2, 6, plus 7, plus 1, it's still 7/8 power. Then let's do that. Do we have another one left? Yeah, that one. We have this one left. So square root of 2, square root of 2, square root of 2, square root of 2. So for the first one, that one, it'll be 2 to 1/2 power. The second one, it'll be 2 to 1/4 power. Third one, 2 to 1/8 power. Fourth one, 2 to 1/16 power. Okay? Once again, the base is 2, and then add the powers. This we're using in adding powers and rewriting these radical expressions with rational exponents. And in adding powers, we're using the things we learned in Math 124 and Math 126. If you have if you, as I go through it, if you don't remember those, please do a brush up on those, do brush up on those properties of radical expression and powers. So look up the properties of radical expressions and properties of powers. You can, if you don't have the book anymore, you can Google these two properties, properties of rational exponents or radicals and properties of powers. And this should make more sense. And then take the common denominator, which is 16, and then that would be 8 plus 4, 12, plus 2, 14, and then 15. So 2 to 15 over 16 power. Okay, so now we have, so let's list these. So we have the sequence. That sequence, using this hint, we can rewrite this sequence in terms of numbers that have base 2 to some power. So 2 to 1/2 power, 2 to 3/4 power, 2 to 7/8 power, and 2 to 15 over 16 power. Okay, so now to write the sequence for this, clearly 2 is part of it, 2 to some power, right? So an, the sequence that we're looking for, the nth term of the sequence we're looking for, certainly has 2 as the base, right? That's common for all of those. Now we have to make a connection between the position of these numbers and what happens in the power. So this one is n equals 1, right? Or a1 equals 1, however way you'd like to think of it. That's a1 equals that term, or that number is occurring in location 1. In location 2, we have that. Location 3, we have that number. Location 4, we have that number, right? And of course, let me add here that this is an infinite sequence. I forgot to add that. So this is also an infinite sequence here. Okay, so we're looking to find the power of this 2 in the formula form. So if you look at, for the first location, the 2, how can we get 2? If we raise, we want to tie this power to the location of this. That's how we can create the nth term of the sequence. So let's see if there is a connection between this power and the location of each term. So 2 to first power, which is the location, 1 is the location of this term, 2 to first power is 2. The location of this term is second location, right? So 2 squared is 4, 2 cubed is 8, 2 to the 4th is, so another pattern is emerging, right? So the power here, how can we get this power for each one? So we can do 2 to the n power, right? Sorry for making this a little bit too crowded. It's mixing with that. But 2 raised to some power, right? Let me put the parentheses around it. So we're trying to figure out what that power should be, because 2 is common. If you look at this sequence, 2 is common at the base. We're almost figured out the denominator of that fraction. 2 to the nth power is going to give us that. For the first term, 2 to first power is 2, which is what we have. So, but that, if you compare the denominator with the numerator is always 1 less than the denominator. So 1 is 1 less than 2. 3 is 1 less than 4. 7 is 1 less than 8. 15 is 1 less than 16. Great. So then we can say the same thing, but minus 1. 2 to the n minus 1. And we're done. So let me, this is okay, but it's a little bit lost because the page is getting too crowded here. Let me write it here so it's more clear. So the sequence, the nth term of the sequence is 2 to this power. 2 to the n minus 1. I know this looks complicated. I know that. But if you look at, given this hint helped us a lot. And then we rewrote this expression in terms of numbers of base 2, and we already knew that there was a pattern, right? Just looking at this. Now we uncovered that pattern in terms of powers of 2, base 2. So we knew, looking at these digits, we knew that the 2 has to be present always. So that's that 2 you see here. Then, looking at the power, we need to this is a sequence, so we need to establish a connection between the terms of the sequence and the location when they appear. So the 2 is always there, so we couldn't establish a connection using the 2, but the power changes. So then next we looked at the way that power changes in respect to the location of that term, and the pattern was easy to discover. In the first location, the denominator is 2. In the second location, denominator is 4. In the third location, denominator is 8. That tells us we can write the denominator of that fraction in terms of 2 to the n power, n being the location of that digit. And that's how we came up with that denominator. After that, we noticed that every numerator and denominator are different by 1. So the numerator is 1 less, always 1 less than the denominator. So we said, we know that the denominator is 2 to the n, so let's subtract 1 from it, and we get the numerator. And that's how we arrived at that nth term of the sequence formula. Okay, so it does look complicated once we have it, but to get there, it wasn't that difficult. Okay, so we have come to the conclusion of the topics in section 12.1, and as always, thank you for persisting through these videos. Please feel free to ask me any questions you have about this, and I'll be happy to answer those for you. And for now, have a very nice day, and I will see you all next time.